Welcome to physics class. The subsection of discussion is temperature dependence of resistivity. According to the book of NCERT, in NCERT book, these subtopics has been discussed in the page number 103, part 1. Page number 103, 104, etc. Now, we know the expression for resistance R. R is equal to rho L by A, where L is the length and rho is equal to resistivity. Resistivity and or it is called specific resistance. It is called specific resistance. Now, when suppose the temperature of the conductor is capital T, we are considering a conductor like this. This is the conductor having length L, area of cross section is equal to A, and rho is the intrinsic property of this conductor. That means the value of rho depends upon the material. Okay. Now suppose the value of rho is equal to rho naught. Resistivity is equal to rho naught when temperature is 0 degree centigrade and resistivity is equal to rho capital T when temperature is equal to T degree centigrade. It may be centigrade or Fahrenheit. Then the relation between rho T and rho naught is like this. Rho T is a suffix is equal to rho naught into 1 plus alpha into T minus T naught. Temperature is equal to T naught degree centigrade or Fahrenheit, it may be. Bracket closed. So this is the relation between the resistivity at temperature T, degree centigrade or degree Fahrenheit, at a temperature T not degree centigrade or degree Fahrenheit. But if this is expressed in centigrade, then the value of alpha will be fixed. If this is expressed in Fahrenheit, then the value of alpha will be changed. Now, if we put this relation in above equation, in this equation, then we will get RT is equal to rho T into L by A, and R naught is equal to rho naught L by A. That means L by A can be replaced by L by A. L is equal to length of the conductor, A is equal to area cross section of the conductor, and these two values depends upon the geometry of the conductor. L by A is equal to, from second equation, R naught by rho naught. So RT is equal to rho T. Rho T is equal to, rho T is given here, and L by A, in place of L by A is R naught by rho naught. Rho naught 1 plus alpha into delta T into R naught by rho naught. Rho naught cancels. That implies RT is equal to R naught into 1 plus alpha into delta T, where delta T is equal to T minus T naught. This is the temperature difference. As alpha is greater than 1, RT is greater than R naught for that means the resistance of any conductor at temperature T that is higher than the 0 degree is greater than the resistance at 0 degree. That means with the increase of temperature of the conductor, the resistance of the conductor also increases, and this is the equation. This is the equation that governs particularly. This equation governs the relation. So we can write RT is equal to R naught into 1 plus alpha into delta T. Alpha is known as, temperature coefficient of resistance this value is not fixed tolerance for all conductors. So, if we plot a graph that shows the variation of resistivity or resistance with the increase of temperature, then we will get such graphs like this. Suppose this is the x-axis, this is y-axis, this is the x-axis. Sorry. X-axis, y-axis. Along x-axis temperature, along y-axis resistivity, and the graph will be like this. And this graph, this is rho naught at temperature T is equal to 0, and when temperature increases, it increases. And this particular graph is for copper. For copper. And for nichrome, if we take similar graph for nichrome, this is x-axis or temperature axis, this is rho, resistivity axis, it will be straight line like this for nichrome. So when this is straight line, this is straight line, that means the variation of resistivity for nichrome is regular and variation of resistivity of copper is not regular like this, it is straight line. And due to this cause or due to this type of variation of resistivity in case of nichrome, for experimental purpose in our laboratory, we take nichrome wire, and nichrome wire is suitable for measurement of temperature variation of resistance. Now, in both cases, in case of copper and in case of nichrome, in both cases, we see with the increase in temperature, when temperature increases, the resistivity also increases. At higher temperature, resistance is higher or resistivity is higher. In this case also, in case of nichrome, at higher temperature, the resistance and resistivity. Both are higher. But in case of semiconductors are germanium, silicon, etc. etc. The case of germanium or silicon or any semiconductor is like this. Suppose this is y-axis and this is x-axis. That means this is rho or resistivity axis and this is temperature axis. And the variation is like this. As temperature increases, the resistivity decreases. So just opposite phenomenon happens here. When temperature is increased, the resistivity in case of semiconductor for semiconductor. Now why this happens? What is the cause of such variations in case of copper, in case of nichrome and in case of any semiconductor? Semiconductor may be germanium or silicon, etc. etc. Now, if we want to discuss about the nature of different type of variations for different type of conductors and semiconductors, we have to go through the previous lecture. I suppose all of you have gone through the previous lecture, and in the previous lecture an important the expression for resistivity the expression for resistivity from the microscopic point of view, rho is equal to m by n is square tau. N is square tau. Okay. Once again, I want to remind you about the matter of discussion of my previous lecture. Already it has been uploaded, and I suppose you have been watching this or already you have watched this. So the meaning of the variables here, m is equal to mass of electron, mass of electron. N is equal to number density of charge carrier, charged particles that carry that is responsible for electric current. So I have to correct this. The number in charge particles that is responsible, or those are responsible for electric current. And E is equal to electronic charge. You know, E is equal to electronic charge. And tau is equal to relaxation time. Time. Relaxation. Once again, I want to remind you about the relaxation time. We have already discussed this. Suppose this is the electron. This electron moves inside the interior part of the conductor under action of the electric field. Okay. And when this electron moves, it encounters with positively charged ions. The positively charged ions are fixed. The position of the positively charged ions are fixed inside the conductor, and there are so many positively charged ions through which the move. Electrons move from one point to another point under action of the electric field or under compulsion of the potential difference. So, the relaxation time is defined as the time interval between two successive collisions. Suppose the electron is coming from here and encounters a collision here, and then it is deflected towards this and encounters another collision here, then it is deflected towards this, suppose, and encounters another collision there. Okay, and after hitting this point, it moves along this line and again encounters another collision here. So one collision, after second collision, then third collision and fourth collision, the time interval between successive collisions is equal to tau. Now what happens to this time interval when temperature is increased? Actually, when temperature is increased, the behavior of the electron inside the conductor is like the gas molecules to some extent. So there is a very fine difference between the movement of the electron inside the conductor and the movement of the particles or the movement of the molecules of the gas. So here we consider the when temperature is increased, the electron is agitated. That means electron moves with comparatively larger speed. So when this speed is higher, relaxation time, suppose you are moving inside. So I am once again I am reminding you the analogy I have made in my first lecture. You are the electron, you are crossing this playground, especially of the Bakura Hindu High School. You are crossing this playground from one corner to another corner, and this ground is infested, I am uttering the language or word consciously, infested by some antisocial elements, and they are particularly at night. You have to pass this ground smoothly because they are present there. So when you cross this ground with comparatively larger speed, then the encounter of the difference between the two successive collisions will be less. That means at higher temperature, the gist of this discussion, they may be social elements or anti-social elements. That is not the matter of the physics. Let it drop. But the actual gist of our discussion is like this: when temperature increases, when temperature of conductor increases. The relaxation time decreases. So when this decreases, tau when decreases, the value of resistivity it increases. And due to increase of resistivity with the increase of temperature, the resistance of the specimen also increases. And that is why we get a graph like this. The resistance or resistivity rho and temperature T. With the increase in temperature, the resistance or resistivity increases. So this is the actual aim of our previous discussion. I wanted to enlighten you about the interior behavior of the electrons inside the conductor and the cause of the resistance. And now, so what happens when we take a specimen of semiconductor? Now, semiconductor is the matter of modern physics, and perhaps you have to wait a few months to learn modern physics. Now, I am discussing very briefly about the semiconductors, the behavior of semiconductors. So, in case of semiconductors, in case of semiconductors, charge particles are electrons and holes. There are two types of charge particles. One is electron, that is negatively charged, electron that is negatively charged, and holes, those are taken to be or considered to be positively charged. You will learn it later. Now, with the increase in temperature, the charge concentration, the concentration of charge, the number of charges will increase. That means when we have the relation, we have the relation rho is equal to m by n square into tau. So when this factor n, number of charges per unit volume, this increases, this decreases. So in case of semiconductors, the number density of the charge carriers responsible for electric current increases with the increase in temperature. So when this factor n increases, rho decreases, and with the decrease of rho, the value of resistance also is decreased. Okay, so this is the explanation. This is the explanation for the behavior of conductor and temperature dependence of conductor and the semiconductor. Okay, now depending upon the our knowledge already about the semiconductors and about the conductors and about the temperature difference, we have to solve some of the problems like this. I am writing a problem here. The resistance problem. The resistance of a platinum at the ice point is 5 ohm. At C point is 5.22. 5.23 and inside a hot bath and inside a hot bath the resistance is 5.795 ohm. Find the temperature of the hot bath. So before solving this problem, we have to discuss about the working principle of platinum resistance thermometer, and we have to acquainted with the rule properly. So we have already discussed or deduced the relation RT is equal to R naught into 1 plus alpha into delta T, where delta T is the temperature variation. Now, suppose there is a platinum wire and this platinum wire is taken like this in a form of resistance. So this is the platinum wire and it is connected with a battery and a switch or key. This is called key. We can connect or reconnect. Actually, this should be here. This is the key. This is the battery. This is the resistance. And if we can measure the value of voltage, potential difference between two terminals, this can be measured with the help of a voltmeter, and there is a voltmeter here. It will measure the voltage developed between two terminals of the resistance or platinum resistance, platinum wire, and a another device that is known as ammeter, and this ammeter is connected here. Measure the current. To measure the current, this voltmeter is ammeter, and this circuit will give the resistance of this platinum thermometer or platinum resistance or platinum wire. We can measure the resistance of this particular wire at a particular temperature. Now, suppose when this resistance is kept inside a ice chamber means it is covered with ice, that is called resistance of platinum wire with a platinum resistance thermometer at ice point. Ice point means the whole chamber is covered, whole chamber is filled with ice. That means at temperature T, at temperature 0 degree centigrade, R is equal to R0 is equal to হচ্ছে 5 ohm. At steam point means the chamber is filled with steam, that means 100 degree centigrade temperature. That means at steam point, resistance is equal to R100 is equal to 5.23 ohm. Okay. And inside a hot bath, when this same setup or this same body or the resistance is kept inside a hot bath, the resistance of this is measured 5.795 ohm. That means RT is equal to 5.795. Okay. So these are the data. Now we can say R100 is equal to R naught into 1 plus alpha into delta T means the temperature range from 0 degree centigrade to 100 degree centigrade. That is equal to 100. And RT is equal to R naught into 1 plus alpha into T. So these are the two relations derived from directly from this relation. This is the original relation, original formula, and from this original formula we can derive these two equations, equation number 1 and equation number 2. Now from equation number 1, R100 is equal to R naught into 1 plus 100 into alpha RT T is the temperature of the unknown bath, is equal to R naught into 1 plus T into alpha. These are two equations. Equation number 1 and equation number 2. From these two equations, we can directly write the value of T is equal to minus R naught, RT minus R naught by R100 minus R naught into 100. So these two equations gives this formula, and we have already four values are there, three values are there. RT is equal to 5. R naught is equal to 5. R100 is equal to 5.23 minus 5 into 100. That is equal to 345.65 degrees centigrade. Now you notice here the temperature of the unknown bath is 345.65 degrees centigrade. So in case of measurement of higher temperature, we can use this device, though the device not like that arrangement. It is a different device. There is another device known as platinum resistance thermometer that can be inserted or that can be connected with the circuit, and the circuit will show you the resistance of the circuit. You can reduce the resistance of the that wire inside the platinum resistance thermometer, and the variation of resistance should be collected from different data. That means the value of RT, that means the value of the unknown bath, resistance at unknown bath, and ice points, that means you have to insert that thermometer inside ice, and you have to also insert the thermometer inside steam. And this is a tedious practical work. Those students who want to study physics, you have to handle such instruments, and the total process is really accelerating. And there are so many problems related to this formula. Now, page number 127, problem number 3.5 and 3.7. You may go through the book of NCERT Physics for class 12, volume 1. And I have taught this or discussed this topic from the page number 103, 104, and 105. These three pages, we may go through these three pages of this particular book and consult the whole episode and solve the problems independently. And next day, I shall discuss about the only problems of series and in class 10 you have already studied the nature of series connection and parallel connection of the resistances. Those students who are not acquainted with the particular matter may consult the videos made for class 10. Those are already uploaded, and those videos will help you to learn about the nature of parallel and series connections in detail. Though I am giving a brief discussion on series and parallel connection of resistances, because there are so many problems. There are so many problems, difficult type of problems, different types of problems related to parallel and series connection. Now, a brief discussion is necessary before solving such problems, and this brief discussion will help you to solve those problems also. Suppose there is a resistance R1 and another resistance R2 and another resistance R3. These three resistances are connected in series in such a manner. This is the battery, and electric current will go. This I current will flow through this number 1 resistance, number 2 resistance, and number 3 resistance. There are 3 resistances. The same current will flow through 3 resistances, and this is series connection. In case of series connection, the equivalent resistance, that means if we replace these 3 resistances with a single resistance, we take another resistance R, that will replace all 3 resistances and contribute same effect. Then this resistance will be called the equivalent of these 3 resistances in series. And we know the value of R will be equal to R is equal to R1 plus R2 plus R3 in series. And if the connection is made like this, suppose there is one resistance, another resistance, and this is another resistance. These three resistances R1, R2 and R3, these are connected in another mode, R1, R2, R3, and a battery is connected, or cell is connected with the circuit. Then this type of connection will be called parallel connection. And in case of parallel connection, if we replace these three resistances with a single resistance, suppose these three resistances will be replaced by a single resistance, that is R, and this R will contribute the same effect as the effects of the three resistances separately. One resistance is sufficient to produce the same effect. Then this resistance will be called the equivalent resistance, equivalent to these three resistances connected in parallel. And then we can say or write 1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Actually, in parallel. The detailed proof of this relation and this relation are already discussed in class 10, and a separate video has been done to prove these relations elaborately. Those students studying in class 12, but those are they are not acquainted with the relations, they may consult that video and attend this class, next class. In next class, I shall solve problems related to series connections and parallel connections. So thank you very much for watching this video, and this video ends here.